for the set of problems. My name is Hohmuth. I'm from Concept in Germany, and I'm going to present you a hypervisor solution that's fit for use in automotive and other safety-related and security-related domains. And the title of my talk is Preventing Linux in Your Car from Killing You. And it's talking mostly about our L4Re microhypervisor, but also about microkernels in general. So what's this talk about? I'm going to talk a little bit about why just Linux is not sufficient for safety and security critical applications. And I'm going to ramble a little bit about why microkernels are cool this year. They actually also have been cool last year already, but you didn't know that. And why L4Re as a microkernel is especially cool. Then I'm going to talk a little bit about what my company Concept does regarding security and safety certification of this open source L4Re hypervisor, and how certification and open source can mix. So what's the problem? The problem is that software is buggy and that complex software has many bugs. So what we see nowadays is stuff like that, where people break into Chancellor Merkel's phone because, you know, it has bugs. Or people break into your car because there's an over-the-air interface that allows you to access critical functions in your car. Or you might have someone disrupt your nuclear program. Actually, this is a nice photo because you can see the centrifuges failing in real time on this photo. So I don't know if you want this to happen to your country's nuclear program. Or you might have something like robotics, where you have to follow certain safety regulations in order to not get hurt by the robots that build your stuff. Or you might actually have a car that runs a safety critical function, such as autopilot, and maybe it doesn't work all that well, it has bugs. So what do you want to do? What can you do? The solution is that we have to find a way to isolate the complexity of our applications from the critical parts. So if you imagine that you have a system where you have an operating system running some complex applications, such as object detection in a car, and then you have this critical piece of safety-related functionality there that actually can switch the system to a safe state in case something goes wrong. What you want to do is you don't want this critical part here depend on that complex application and that regular operating system, such as Linux. You want to have isolation. You want to move this out of the complex system. You could use extra hardware for that. You could move that safety critical part to some extra hardware, but that creates a communication problem that you have to solve. So it's best if you could do isolation and complex applications on one single platform. And in order to achieve that, you have to have some kind of safe and secure gateway between the two kinds of components. And that's what we actually provide with a virtualization or microkernel solution. In our case, the L4Re microkernel. So this is just a very high-level view and high-level motivation.
Can you just move this to the side without destroying it, if possible?
Okay. Oh, yeah. Let's do that. So if you do that, your application and your operating system can crash all the way at once. It won't affect your security or safety critical part over here. So the problem is that these complex applications are really, really hard to get right. They comprise millions and millions of lines of code. They are really large. And there are statistics that say that you can expect between 20 to 50 bugs for every 1,000 lines of code. And that means that in such a system, you can expect hundreds of thousands of bugs lurking, waiting to be exploited, waiting to crash your system. And what you want to have is, you want to have a trusted computing base that's several orders of magnitude smaller, such as L4Re or another microkernel. L4Re comes with a trusted computing base that can be smaller than 30,000 lines of code, which is, as I said, at least 2 orders of magnitude smaller. So what is a microkernel? Let's start from what you already know. A regular monolithic operating system, such as Linux, runs applications in user mode, your shell, your graphical window system, your application, and then all the operating system stuff is running in the kernel in privileged mode on the CPU, which means that if there's a bug somewhere in there, then potentially your system can be exploited or can crash. And as these regular operating systems run drivers in privileged mode, and drivers happen to be the most crash-prone and error-prone components of the entire system, this means that you're pretty vulnerable if you run it in that way. So what microkernels do is they move the boundary between user mode and privileged mode way down and run only stuff that really needs to run in kernel mode in that mode. And all the other regular operating system components run as user mode applications and are isolated among each other. So when microkernels were invented in the 80s or maybe even 70s, there was a lot of hype around them. Many promises were made, such as that they provide strong isolation and good protection of OS components. They can have a minimal trusted computing base. You can have small components that can be validated in isolation and are much smaller and therefore also easier to validate. You can customize them. You can use just those operating system components that you need in your system. You can run all operating system services as user-level processes, which makes them easier to debug. You have well-defined interfaces because you have to communicate among the operating system components, so you have to think about modularization and interfaces. You can have multiple personalities, so you can run applications from many different operating systems on one system, and they are very flexible and extensible because you can load stuff at runtime or throw it away at runtime. So of these promises that were made in the 70s, 80s, I think not all of them have worked out all that well. So for example, there have been experiments with multi-personality OSs in the 80s, such as with IBM Workplace OS, that have been huge failures and which contributed to the prevalent view today that microkernels are something stupid, something we don't do anymore. So, and if you look really closely, we also know that starting from the bottom here, that Linux, for example, really is flexible and extensible. And it actually is a multi-personality OS. It can run applications from many different operating systems. And actually, it's not all that badly designed. It has well-defined interfaces in the kernel. So I would say that at least the bottom three of those is stuff where monolithic systems have catched up and that aren't valid reasons to choose a microkernel-based system today anymore. But I think that the other properties actually are good reasons today to use microkernels. We want to have the isolation properties and the minimal trusted computing base. We want to have easily validated small components, and we want customizability. So I'm a representative of the L4 family of microkernel-based systems. Here's just an attempt to shed some light on the history of L4, which has been starting at the end of the 80s, starting with a system called L4Re. And then there have been many different iterations of the APIs and the implementations of L4. And this afternoon, you will get a talk from Gernot Heiser, presenting one of those contemporary L4 systems, L4. I am talking about a different line of development that happened in Germany at Dresden, which yielded our L4Re system, and which came out of the University of Dresden. So we started in '97 with a lot of academic research in virtualization, in real-time, and in security-related issues. And CamConcept is actually pretty young. As a company, we were founded in 2012, and we have started the company actually in the security consulting business. So high assurance security applications were the first ones that commercially used our version of the L4 microkernel. So we've been working with certifications and with application approvals by the German security certification agency, BSI, and that has been our business so far. Then as a next step, we are also looking into other certification-related application areas. So right now, we are tackling automotive. I'm going to talk more about that later in the talk. And after that, we'll also go into the industry safety market. And there will be, aside from our open source version, there will also be certified commercial versions that you can buy together with the required certificates for your application area. So over the years, a nice bunch of technologies has been developed. And here's just a very high-level overview that shows you what the system structure looks like, much like the diagram I showed you before. We have just the microkernel and microhypervisor running in the kernel space, and then we can run virtual machines and also native micro apps in isolated compartments. And we support various different guest operating systems in virtual machines. And then we also have something called the L4Re runtime environment, which provides the capability to easily develop native applications with a very small trusted computing base that use a subset of POSIX, so they're easy to develop as well. And then you can run, for example, native drivers or security critical stuff or real-time stuff directly on top of the hypervisor and don't have to trust the legacy monolithic operating systems anymore. You can still use them for your functionality, but you don't have to trust them anymore. That's what we want to achieve. So a few keywords here. We support 3 different architectures, x86, ARM, and MIPS, all in 32 and 64-bit modes. We support hardware-assisted virtualization and para-virtualization, more on that later. We support both dynamic and static setups. With dynamic, I mean that we can start, instantiate, and shut down components at runtime dynamically. We provide very strong isolation. We have real-time capabilities. The virtual machine monitor supporting our virtual machines is also actually untrusted, and also more on that later. We do have a POSIX subset for native micro apps. It's all open source, and it's a pretty major system because it's been used and developed over the past 20 years. So let me talk about some of the noteworthy features that L4Re has. The first and most important one, of course, is the isolation feature I mentioned. So L4Re participated in the last evolutionary step of L4 microkernels and nowadays is a capability system. That means that we have capabilities as protected kernel objects that are used to reference other kernel and userland objects. And using capabilities, we get 2 important features. The first one is information hiding, because capabilities provide local names for all system resources. That means that if you don't have a capability, you can't even name a resource that you might want to communicate over or that you might want to use to crash something. And they also provide access control, because again, if you don't have a capability mapped to your task or virtual machine, you can't access that particular kernel object. Capabilities are also nice because they enable reasoning about isolation and freedom of interference. So basically you can show that if you don't have a capability to any shared object with another compartment, then there's actually no way to communicate with that other compartment or to interfere with it. L4Re is designed to even allow sharing prevention for second-class objects, so objects that don't have capabilities that are hidden inside the kernel, such as allocators, for example, and also invisible architectural state, including caches and TLB state, for example. But I have to admit that we're not 100% there yet. It's also not needed for many use cases because we have features that allow us to isolate on higher levels. But I just wanted to mention that we think about isolation very, very hard, very deeply. Another noteworthy feature to talk about is the real-time capabilities. L4Re is started out as a real-time system, and it provides a real-time scheduler for each CPU. All of them then use fixed priority round-robin scheduling for real-time. Right now we are adding thread group budget scheduling, and we also support some kind of non-real-time weighted fair queuing scheduling mechanism. What's also noteworthy about L4Re is that we do support thread and virtual CPU migrations. So you can implement something like load balancing or scheduling on user level and schedule stuff around on your physical CPUs. L4Re is real-time capable because it has only very short critical sections where we turn off interrupts, and where we have longer running stuff inside the kernel, we have preemption points. We have a finely granular locking system that allows the system to scale really well. And the locking is actually weight-free, even if you have to grab a lock that's held on another CPU, there's an upper bound of wait time that you have to spend in order to get access to that shared resource. But normally there is no shared resource. If you run locally on your CPU and avoid doing stuff that might affect other applications running on other CPUs, then there's no shared data anywhere, and so there's also no performance dependency. And we don't have any big kernel locks that would prevent us from scale. The third thing I want to talk about are the virtualization features. L4Re supports hardware-assisted virtualization on all the three architectures that we support. And one specific nice thing about our system is that even the platform emulation support, so that, for example, QEMU or whatever you use to provide the illusion of a virtual platform to your guest operating systems, even that component runs as an untrusted user mode application. So that's a difference perhaps from Zen, where you have to trust DOM0, and inside DOM0 there's an entire Linux kernel running QEMU, and DOM0 needs to be trusted by all the other domains, including the critical ones. That is not the case in our system. So all the VMMs only have a trust relationship with the virtual machine that they serve. We actually have various different virtualization solutions. So one of the VMMs that we support is called UVMM. It's a tiny VMM that's designed to just support Linux guests. And it can be tiny because it provides the necessary APIs that allow Linux to run as a guest. So, for example, it provides virt.io devices for all the necessary device classes and a single boot protocol. And on ARM, actually the state is really cool because we can download an ARM Linux kernel from upstream and configure it with virt.io devices, and it just runs. There are no modifications necessary. It's just supported out of the box. Another virtualization solution, or another VMM that we support, is called L4KVM. That's support of KVM to run as a user mode application, which uses QEMU with KVM and Linux guest to provide the platform emulation support. We use that to support Windows guests. Another virtualization solution that we support is called L4Linux. It's our para-virtualization solution. So we use that. L4Linux is a port of Linux to run as a user mode program on top of L4Re. And we use that to provide Linux virtualization even on platforms that do not support hardware-assisted virtualization. And there's also a surprising number of use cases where para-virtualization is actually nice, or actually having a user mode Linux is nice, because, for example, such a Linux kernel running as an application program can serve as a client or a server for other natively running applications on the system. And that use case is pretty common because Linux has so many device drivers. So we often use it as a device driver OS, or a device driver driver, providing services to native applications. The fourth thing I want to talk about are the native applications, the micro apps as we call them. So micro apps are applications programmed directly towards the microkernel APIs. And that way you can implement critical components that are really, really small, have a really small trusted computing base, and have no dependency on any rich operating system such as Linux, or a DOM0 running Linux or anything like that. And native applications are also nice because they come without any visualization overhead, because they just run natively as native ring, userland applications. We support a programming environment for native applications called L4Re runtime environment, which supports a subset of POSIX that you would expect. So we include a C library and a C++ library. Actually, most of our systems implement in C++, so we support C++ really well. including all the dangerous stuff, like exceptions and runtime type identification and stuff like that. We have a pthreads library and many other things that you would expect from an embedded programming environment. The L4Re runtime environment actually is a native or a natural extension to our kernel API. You can't really tell the difference whether you're talking to an L4Re runtime environment object or a kernel object. The interface is the same, and you can even have one mask another or one proxying another, which is a nice design pattern that we support. And we use the L4Re runtime environment, for example, for things like that you normally don't care about as an application programmer, such as address space management. Normally, that needs to be all done by your application itself. So L4Re, the microkernel, provides the mechanisms to implement paging, for example, or shared libraries on your own, on userland, and L4Re takes away that work from you and just provides you with a default implementation. Another thing I wanted to talk about is I/O virtualization. So what L4Re can do is it can allow pass-through device access so that userland drivers or virtual machines can access devices directly and use their drivers inside the virtual machine. And in order for that to be secure, you actually have to care about DMA, because usually devices have direct memory access. They can access the entire physical memory. And to prevent that, you need an IOMMU, which virtualizes the address spaces that the devices can see. And L4Re supports that as well. We have native drivers and multiplexing drivers for various devices and buses, including PCI, serial, AHCI, and frame buffers. And we also support virtual networking among virtual machines. So you can have a virtual Ethernet connection or even virtual Ethernet switching among various virtual machines. And we also support something that does not have IP overhead, but still allows inter-VM networking, which is an L4Re specific virtual socket implementation. And all of that is based on the virt.io standards. So any guest that supports virt.io, including Linux, Windows, QNX, feel well as guests on our system. As I mentioned, L4Re is open source. You can download it from our website. Nowadays, we publish snapshots of our internal development versions. Internally, we use Git, and soon we will also make available our Git histories for anyone who is interested on GitHub. But that's right now still being set up. So, open source means we have to talk about licensing. L4Re is mostly licensed under GPL version 2. But one special thing is that we also offer commercial licenses. We do have dual licensing capability, and that's why we require contributors' license agreements for all contributions. The reason we do that is that we have to be able to commercially license our system in order to attract the investments that we need for certification. That's basically part of our business model. And I'm going to talk about more about that a little bit later. And also, having available commercial licenses is a requirement for some target markets, including automotive. So we know that the OEMs, the actual car manufacturers, don't like to use open source software. Of course, they would like to use the features, but they don't like the licenses for various reasons. And that's why it's cool to have a commercially available system as well, even if it's also open source. In L4Re's case, our company, CanConcept, serves as the maintainer and gatekeeper for all contributions. And that is also a requirement because we care about the quality and integrity management that is needed for the certification projects that we do. Okay, let me show you some of the use cases we are supporting today, and then some of the use cases that we will support in the future, including automotive. So today, well, that actually was yesterday in the 90s. Well, it was the first commercial application of our L4 system in an ebook reader, ironically used for digital rights management. So that was the first thing that paid for some of our coffee when we still were a university lab. then we actually were participating in one of those secure mobile phone projects that we had in Germany. So there was a project called SFO17-416 that provided a virtualized Android experience where there were 2 instances of Android running on one phone. One used to securely VPN into the government network and do secret phone calls with government proprietary crypto. And the other one to dial into the hotel Wi-Fi, browse Facebook, and use Twitter and so on. It was a really cool product. Unfortunately, it was discontinued. I don't think there ever was a use case for it. But it was a really nice product. Business case, I mean. Here's one of the marketing slides from Deutsche Telekom that showed how you were able to switch seamlessly between the 2 virtual instances of Android running on the same phone. Another commercial application nowadays that we have is a customer called Genua. They provide a very similar application, but on a laptop, running 2 virtualized instances of Windows. Again, one for securely VPNing into the government network. They actually integrated a hardware-based VPN solution that they previously developed to run as a micro app on top of our hypervisor embed system. And the other virtual Windows instance you use to down to the hotel Wi-Fi. Another use case we support is data diodes. Data diodes are appliances that you put in front of your network access and that make sure that you can browse the web, but no bit of information ever leaves your network. And so this company, I think this is also Genua, Genua, they provided a system where they have a filter that runs a very small trusted micro app that's just a few hundred lines of code large that implements the filtering mechanism that prevents bits from leaking out of the internal system. And then there's another customer, Infodas, who builds a product called Security Gateway, S.Security Gateway, that's used to connect government networks that have to protect classified data to the internet or to less classified networks. So they always talk about high and low domains in red and black. And between those 2 different kinds of networks, you put this application gateway that screens all traffic coming out from the internal or highly classified network and makes sure that only approved stuff, approved emails, approved data can ever leave that network. So they switched to L4Re because there was a requirement from the German certification agency for this kind of application, the BSI, that they have to use a trusted runtime platform, and they selected our solution there. So let's look at some of the future use cases. One of them, just to showcase it, we have a customer who builds home appliances, because you know your refrigerator has to talk to the internet as well these days. I don't know why, but
Oh, the beer.
and but still, they are opening an attack surface towards the internet, but they have to make sure that it keeps cooling, that it keeps running its critical function, and that's why they have to have some kind of isolation. Microkernels work well for that. So let's talk about some of the certification projects that we do. The first one is actually not safety related, it's security related. It's a project we already started. We are planning to do an common criteria L4+ certification. These certifications are not really a hard requirement for the application approvals I talked about earlier from the BSI, but they do speed things up because they provide the same information that these approvals require. And so to easily and quickly port new applications and make them available inside classified networks, it's nice to have a trusted platform that is security certified. And that's what we're right now doing. So let me talk about this business aspect of it, the licensing model. All the code that we do for that project will still be open source, but we will keep some of the certification documentations, some of the tests, and some of our quality assurance tooling that we require for the certification proprietary. And this is to protect the investment, the considerable investment that we and our sponsor are investing into this project. This needs to be protected, and therefore there has to be something that does not allow anyone to redo the certification easily, even though the code is open. So in that particular case, our sponsor gets the exclusive commercial exploitation rights for the government market only, and CAN-Concept retains the commercial exploitation rights for all other markets. So that's a typical business model that we use for certification. Let's also talk about automotive, which is a really hot topic within our company right now. So we are right now starting an ISO 26262 certification process to achieve the automotive safety integrity level D, which is the highest one. And it will certify L4Re as a safety element out of context, so without hardware, abstracting away from the underlying platform, just the software component will be certified. And ASIL actually is a hard requirement for many OEMs, especially for the high volume automotive markets, so for passenger cars, basically. The licensing model should look similar, should look familiar to you. So all the code will still be developed as open source, but we will keep proprietary some of the certification documentations and tests and quality assurance tools. And again, our sponsor, I'll talk about him in a second, gets exclusive commercial relicensing rights for the automotive market only. And we, CAN-Concept, retain the commercial exploitation rights for all other markets. So we managed to get into a nice partnership with a big tier 1 software supplier. So we have the buy-in, they will provide the investment needed to do the certification. And I think having such a relationship is really important because this allows the OEMs, the actual car manufacturers, to buy from a trusted source. The tier 1 assumes most of the risk that comes with the use of such an automotive hypervisor. They can cover the liability issues that come up and can indemnify the OEMs. So if there's ever a recall, it's not that CAN-Concept will go bust. We're a small company, we can't really stand in for these kinds of risks. But they can, and that's important in the automotive space. And also, they can provide the closed source instance that is required in the automotive market because the OEMs trust closed source more. We can talk about later on the Q&A if you want about the reasons for that. So, but still, open source will benefit from this partnership because everyone can basically start their research or development starting from the open source version. They can download it from our website, and if they can also do their own certification if they have to. But if they want to have a quicker path, they can just buy the certified version from our tier 1 automotive partner. Another certification project we are planning to do, we haven't started yet, is industrial safety certification according to IEC 51608. And there we are shooting for safety integrity level 3, which is the second highest integrity level you can achieve there. And it's actually also a hard requirement to have certification like that in order to allow the use of hypervisors in industrial safety contexts. The licensing model, again, should look familiar, but it's not that fixed yet because we don't have a sponsor for that project yet. We will develop the code base in the open source again. We will keep the certification documentation proprietary, but we haven't finalized yet who will be the sponsor and who will get relicensing rights. Maybe we will even do this ourselves. We believe that the delta between automotive safety certification and industrial safety certification is not all that big. We could even stem that ourselves as a small company. But still, we are soliciting requirements right now and are looking for partners who help us finance, build, and distribute such a product. And we already have a good distribution partner who knows all the customers. Okay, so I talked a lot about open source. Let me talk a little bit about what we as a community, we as an open source community could do to invest into the system, despite CAN-Concept providing that gateholder function for the certified code base. So some things that we could work on together, for example, are portability issues. The community could provide platform support for platforms that we don't support already. We have issues with portability issues with regards to power management and to especially clock networks on the platforms. Those could be abstracted away and unified, and we could support upcoming firmware interfaces that take away some of these daunting tasks from our system. Then the community could also be involved in providing a better user or developer experience for our system, working on the usability from a developer point of view, and working on the documentation to get this up and running. And also, we would like to work more on security hardening, but it's a hard sell to work on that. Our customers are happy with the level of security we already provide, but there's always more that could be done. So we do have an interest into using formal methods, static analysis, to get to a higher level of security and maybe also safety, and to provide even better isolation for new attacker models that might come up. Before I summarize, I'd like to thank you. So first, I'd like to thank Gennaro for inviting me to this conference and giving me the opportunity to talk about our automotive activities and about our hypervisor in general, present this to your community. I'd like to thank ARM to providing many interesting conversations and connections and insights into your company, and especially to Robin for facilitating all of that. So thank you. And then just a summary. So why do I think is L4Re one of the best solutions for providing functional safety in an open source space today? Well, first, it is actually open source, which is an important differentiator. Then it is a major high quality implementation with a rich feature set. I hope I could introduce you to some of the outstanding features that L4Re supports. We provide a platform that does not require any trust into a legacy platform, such as, or not legacy, in a monolithic large code base, such as Linux. There's no trust dependencies that would have to be removed first, such as would be the case with Zen. It has been built from the ground as a certifiable, safe, secure solution, and there's no need to strip away stuff. One additional benefit is that for L4Re, commercial licensing is available. I tried to highlight why that is an important factor. And also, we already have partners who can take on liability coverage, which is also very important for automotive. And I think I showed you some ways of how we try to arrive at a solution that has both liability coverage and still is open source. For certification, CanConcept serves as the developer who covers quality management and the development process requirements needed for certification. And we think we have created a unique business model that actually attracts the investment needed to do the certifications in the first place. And with that, I'm finished. Thank you for your attention. Any questions?
Yeah.
There's also a mic.
No. It seems like a lot of what you talked about, there's a good overlap with what a trusted execution environment is on the ARM platform. You make no mention of trust zone, so I assume you're not using any of that. So my first question is just, can you confirm that you're doing all of this without using trust zone? And the second question is, have you looked at taking that a step further and looking at getting global platform API support so that something like a traditional trusted agent would be able to run on this platform?
Good questions, thank you. So first, let me take the viewpoint of an academic operating systems developer and tell you that we don't need trust zone because we have a secure operating system, and if we need to isolate something, we just put it into a virtual machine and its own address space, and it will be secure there. That said, we actually do support trust zone as well. So L4Re can also run as an operating system on the secure side. For example, we do have a monitor that allows switching among the sites, and we do provide interfaces to use trust zone components inside our virtual machines. Additionally, to your second question, we have looked at that, and there's actually a project underway to support global platform APIs as part, inside virtual machines basically, as a compartment, which would allow you to instantiate many of them. You can't just have one of them running in trust zone. You can have many of them for for example, for devices that have many tenants and have different trust requirements and do not necessarily trust each other. So yes, this is an interesting topic. There is some overlap, and the way we look at it is we try to support this and tap into this as much as possible.
You mentioned that you have a few VMM or implementation you can use. Did I get it right that they're running as an application on top of the microkernel?
Yeah.
But if that is the case, does it mean that basically, I mean, do they have, I mean, they set up paging, base table for guests?
Yeah.
So do they basically have access to the whole memory of the system?
No.
How do you solve that?
Well, they do provide paging to the guest, but L4 has a mechanism to do that securely. So what L4 supports is something called, let's say, nested paging or something like that, where you provide for example, the virtual machine monitor with a set of physical page frames that it can access, and it can pass on writes only to those physical page frames it already has, and can put them into a virtual machine or into a task it is serving. So that's something that is protected by the microkernel. There's a paging mechanism in there.
So one last question. So it being dual license, I mean, external contributors, how does it work? And also, do you have maintainers that are not part of the company? As a multi-vendor community, how do you, yeah?
So we do accept contributions, but we require contributors to sign a license agreement, a contributor's license agreement. And this license agreement basically makes sure that everything they contribute will end up as open source, if we ever include it in the system. But CamConcept also has the commercial exploitation rights and relicensing rights for that code. And we do occasionally get very large contributions. So for example, the initial versions of the ports to MIPS and to ARC64 were supported by two external entities. So Imagination supported the initial MIPS support, and HP Labs provided the initial ARC64 support, for example. So we are quite familiar working with large contributors that way. Does that answer the question?
Two questions. One is technical, one non-technical. The first one is memory management, right? So you put memory management actually in runtime. Is there some reason behind that, or what do you think to put this actually in the microkernel to get better performance? So that's the first one. The second one relates to the certification. So we already have a tier 1 customer helping you to go through all this certification for automotive. So for the second or other tier 1s, how that works? Can we use some previous works, and how much will that cost?
So regarding the first question, so L4 historically has always supported implementing paging on user level. And so it was actually, I think, a very successful experiment in providing an API that implements the mechanism for supporting paging in the kernel, but leaving all the policy to userland. So you can implement whatever kind of paging you want in userland as a user application. So of course Linux would via VM or L4 Linux implement paging by doing swapping and whatever Linux does, right? And L4Re, the native programming framework, the L4Re runtime environment that we support, supports paging not for swapping, that could be implemented as well actually, but it doesn't support that right now, but it does support shared libraries of copy and write. So these mechanisms can be implemented on user level. That doesn't necessarily mean that this has bad performance. It just means that, for example, page faults get reflected to a userland program, and this userland program can then make policy decisions on which page frame access rights to map to the task or virtual machine that had a page fault. So benchmarks show that for hardware-assisted virtualization, the overhead is really negligible. I don't think there's any performance overhead that could be, or any performance gain that could be had by moving paging back to the kernel. To your second question, the Second, so our tier 1 partner actually is the software house of a big tier 1. And the construction they use is that the software house is separate enough from the tier 1 that it also can sell its software to all other tier 1s. They provide some of the most used implementations of automotive operating systems that you see around. So, and all tier 1s use them already. So I don't think there will be a trust issue with using that software from within another tier 1. The other tier 1, the second tier 1, could either do certification themselves, starting from scratch, or they could go to that software vendor and just buy the license. There's no real hindrance.
Any other questions? Or sorry.
Thanks, Ron. Just a slight follow-up to that from the previous question. It's about ongoing certification. So, you know, you've achieved certification and then you get other contributions in. Is it just a matter of rerunning some tests and everything's all good, or is this really painful and you have to go through, you know, a periodic process to?
Painful. So what we are going to do is, when we create these certified products, we will fork off a stable version, which will have to be supported for many years to come. Whereas development on our master branch will just continue. And if we redo the certification, it will be painful. But there are some things that we can do continuously in order to ease that pain a little bit. So for example, once we have all the QA infrastructure in place, we can make sure that QA applies to newly developed features, for example, as well. If we have all the processes in place for quality management, we can use them just continuously also for developing our master branch to provide the necessary process requirements when a recertification needs to happen. So we plan to do all that stuff, but I still expect that there will be some kind of pain.
Thanks.
So the reason I requested Michael to come over and give us this talk was because for those of you who saw my update on the kind of like auto BOF, the observation I have is that, you know, there are lots of offerings that are technically sound, but when it comes to offerings that are technically sound and available in the open source, there seem to be few. But when you talk about offerings that are technically sound, available in open source, and have the kind of certification experience required, it boils down very quickly to, thus far I only found this one. So I'm not endorsing anything, but as I want to see options over there. This one looks pretty damn good. I haven't played with microkernels though in my career, so this is a bit of a learning experience for me as well. I think there's the problems kind of solved. The strongest endorsement of the operating system design is the fact that the three biggest proprietary OS vendors are microkernels. This is what they do. So, any other questions, by the way?
So what happens if you have a certified product and then you have a security patch needed in the certified product?
So part of the it's actually a very good question that also that comes up all the time basically. So the certification actually applies only to the broken thing that requires the security patch, right? So that's the certified thing. But certification actually requires that you have flaw remediation process. So you have to have a process to accept to accept security reports, to actually fix them in some finite time space, and to provide updates. And that's also a requirement for the application approvals I talked about. So what they do is they technically require certification for the base, so for a certain version, and then they can live with updates. So that doesn't break the approval.
That's what I would expect.
You mentioned that you guys have some over-the-air update architecture as well. Is that something you have formally, or is that just something you're going to work on?
We have a nice demo. Yeah. So what we can do, I mentioned what we have productized is that you can shut down and restart applications, compartments, virtual machines on the fly. And we have a cool demo where that actually embodies a router class device, a home router, a plastic router, and you have an application on your smartphone where you select additional application needs to be installed on the router. And then you have some cloud infrastructure that sends a command to the router which starts downloading new virtual machines to the router and instantiating them already readily personalized for you. So in that demo, it's something like Spotify. You download the Spotify VM, it's already personalized with your credentials, and it just starts playing to your boxes, to your monitors in your living room. That's the kind of thing that we support. Yeah.
So I did a lightweight evaluation of Linux 3 because Tannenbaum and modern operating systems, microkernels. I had to check it out. They do have an interesting architecture for what they call I think it's a reincarnation server, where they're able to kind of self-heal certain classes of device drivers if they encounter a fault. Do you guys have some kind of a similar thing?
Well, we don't have anything readily available, but it could be implemented. The mechanisms are all there. Actually, that was one of the things that L4Re supported really well back in the 80s, the predecessor to L4. So they already had this kind of stuff where they could. It was also a persistent system, and they reinitialized device drivers when it came back up from a suspended state, and they monitored whether they still worked and restarted them. So all of that is possible, but we don't have any product supporting that right now.
Okay, so if you have the mechanism to certify a security update, can you deliver that security update if it actually affects the microkernel itself over the air? And if so, how securely?
So that's actually something for our users to solve. So what they typically do is they have a VM running that implements the updating process, and that VM has access to the boot image and can receive new updates over the air, can check them, can check the crypto in them, and then writes them to the boot image, and then you can reboot.
Yeah.
So that's something that we really don't care about, actually. But we do care about it, but we don't provide a solution.
Right. Don't care enough about it. That's okay. We are running out of time, so
Sorry. Just very quickly, follow up on that. I guess you don't have a solution for the secure boot story either. Is that the user problem?
That's right.
Yeah.
So
we've got a meeting.
that's also something for the customer to solve, actually.
Yeah. Okay, thanks.
Okay, thank you.
Yeah, thanks very much.